Okay, and I think that's going now, so we can start. All right, so welcome to the class, Spectral Graph Theory. So the first thing we have to talk about with any class is the syllabus. Now this, you'll notice I have two course numbers here, 495/595, so either undergraduate or graduate level. It's the same material, but you'll have slightly different requirements, slightly different homeworks. We'll talk a little bit about that in just a few minutes. Okay, so I'm the instructor. I'm on here somewhere. Oh, I'm down there. Steve Butler. That's me. My office is up in Carver 400C. I do have office hours set aside for this class. So when I say Wednesday from 2 to 4, that is something that my calculus students don't know about. And so don't show up like, oh my gosh, he's going to be swamped by calculus students. No, I'm not. So feel free. And if that doesn't work, just get a hold of me. And I tend to be fairly available. So this course is spectral graph theory. What do you need to know coming in? I expect you to know the basics of linear algebra. You don't need to be super powerful linear algebra people. And so I'll talk about some of these things in a little while. But you should be comfortable with things such as eigenvalues, eigenvectors, rank, characteristic polynomial. Those are words that should not scare you. Or at least you should have heard somewhere before in a mathematical context. I'm sure rank shows up in non-mathematical context. I don't think eigenvalue shows up non-mathematically very often. I'm not assuming graph theory. So if you haven't had graph theory before, that's okay. You'll learn it, or at least you'll learn parts of it. Spectral graph theory does not work well with all types of graph theory problems, but it works well with some types. And so the important things you will learn. The goal of the course is really to understand the interplay between linear algebra and graph theory. And we'll get more into this later on, and there's lots of different things that can happen. Now for the book, there is a textbook for the course, which is an introduction to the theory of graph spectra. It's that book right there, which you can't see because of the glare, but there it is. It's not a bad book, it's a good book. I'll probably go through parts of it. I'll move around as I see fit. It's not the most up-to-date book, because there is no most up-to-date book, because things are continuously coming out, and so we're going to jump around. Sometimes we'll be in the book, sometimes we'll be out of the book and doing other things. And I will say, I was raised in San Diego, at least raised academically. That's where I did my PhD. And in San Diego, they have a very particular type of spectral graph theory. It's the San Diego Laplacian. That's actually not its real name. But anyways, we're going to go into that, and that's not in the book, really, not developed anyway. So we'll mainly start from, that's our jumping off point. Software, students are encouraged, and as it says here, in the most required sense of the word, encouraged, to use software to explore, and they can use it to answer questions. I would recommend Sage. You can get a Sage account on Sage Math Cloud for free. You can also get a Sage account from the Iowa State Sage servers for free. The advantage for the Iowa State Sage server is you can run a computation that goes for a couple days and they don't complain. If you go to the cloud, if you go for more than a couple of minutes, it complains and it'll stop you. So there's an advantage to staying local. I did find out on a fun side note that more Sage computations happen in Iowa than anywhere else. Because, not because of our servers, but because the people who, William Stein, I talked to him at the joint math meetings, and it turns out that the Sage Math Cloud actually is housed in Iowa. And there's a Google has this Google Farm location, and it's in Council Bluffs. And so more Sage is done in Iowa. So, good place to be. The nice thing about Sage is it's free. If you like Mayflower Mathematica, you can do that. The other nice thing about Sage is I can help you. If you have Mayflower Mathematica, I can't do that. Okay. So lectures are Monday, Wednesday, Friday. Obviously, you figured that out because you're here. Yay. Okay, great. There's going to be 2 take-home midterms, a take-home final, homework, and obviously that does not add up to 100. So it must be continued on the second page. Yes, here we go. For the students in 495, that's class participation. Make sure you keep showing up to class because I just want to see you. And I like having people come to class. For 595, instead of participation, it's presentation. So you're going to give a presentation. This is my way of saying, okay, I only have to teach for 12 weeks because 3 weeks the students do presentations. So it works great for me. Talk a little bit down there. 5% is visiting with me. And that will happen sometime in roughly the middle of the semester, the 8th plus or minus 1 week of class. We'll figure out when there's not too many other exams happening so that students aren't busy, and we'll do a sign-up sheet, pass it around. There's a note that I have here. I reserve the right to generously bump up the grade of anyone who comes in and participates. You know, I'm not here to fail anybody. So this is a course more for fun. This is like, let's learn about something interesting. And maybe if you really enjoy the topic, then you can do more on this topic. You know, it really is a nice and alive field. If you don't know that yet, hang around in Iowa this summer. There's something called the International Linear Algebra Society, or just ILIS, and they're holding a meeting here. There's going to be 500 people coming in, and not all of them will be doing spectrograph there, but probably 20 to 40 of them will, and they'll talk about what's happening. And so if this is at the end of the semester something you say, oh, this is so cool, I want to do this for life. Okay, we can do that. Arrangements can be made. Okay, so I'm putting this here to say, look, don't give up, just keep coming. I'm not here to fail anybody, which means, you know, in terms of like graduate students, I'm not here to give anyone below a B. You know, I should be careful not to record that. But anyways, I just keep coming, keep working, you'll be fine. Okay, for the presentation, if you're a graduate student, I expect you to present on a mathematical result. In other words, find a paper that relates graphs and matrices, and find a recent one, has to be published in the last 10 years. There's one caveat: it can't be written by somebody from Iowa State. And that's partly so I can use my own papers when I present. I have some fun results that I'd like to present, but also I want you to branch out a little bit. The presentations will be 15 minutes, which means that I'm not expecting you to do a lot. It turns out 15 minutes is not very much time. It feels like it, but no, it goes by pretty quick. So basically what can you do in 15 minutes? You can state the definitions, give an example, state a result, and sketch a proof. And so it's not meant to be a very onerous thing for you to do. Okay. You can use the chalkboard, or you can use prepared slides, or you can use the document camera if you're really bold. All right. Oh, wow, and it keeps going. Wow. Okay. Anyways, this just says the presentations happen at the end of the semester. We'll sign up sometime in about a month, so you have plenty of time to prepare. And I make sure that no two people are presenting on the same thing. And there'll be more information about that in the next couple of weeks. All right. Any questions about the presentation part? Okay. Homework, it's assigned on Fridays, and you'll get a week to do it, and it's due the following Friday. You can turn it in class, or you can just email it to me by 5 p.m. on the day it's due. There'll be problems which are marked 4 or 5. 4, it marks the 495 students, 5 is for the 595 students, 4/5 is for everyone. I don't anticipate having very long homeworks, probably in the range of 3 to 5 problems per week. And you can work together. You can do all the problems you want, just make sure to turn in the one set, whether you're 495 or 595. You can work together, that's perfectly fine. I encourage you to try to do it by yourself first. There's no penalty for working together, and you can ask the professor who likes to talk about these problems. I will say one other thing about the homework is that if you are in 595, I do expect you to do LaTeX. Or if you're very sophisticated, law tech. I've never decided which one is the right way to pronounce that. Figures you can just draw by hand. 495, you can either use LaTeX or you can write it. As a comment there, any work submitted using Word, will be shredded. So look, don't use Word. It's not worth it. Not worth it. There's 2 take-home midterms and take-home final. You'll notice here, you're like, well, wait a second. Take-home midterms, take-home finals. You can email the homework in. Do I ever have to actually come to class? Well, yes, you have to present. But other than that, no, I guess you technically don't. But you should come anyways. It's fun to come to class. The tests are open notes and open book, but you can't talk to anybody else. And so that's the extent of that. And again, of course, if you're in 595, use LaTeX. And if you're in 495, don't use LaTeX. If you have any accommodations, make sure you make me aware of them. Cheating is totally unnecessary for this course because I'm just, this is supposed to be for fun. If you cheat, as it says here, you lose the ability to add 5 and 7 and spend the rest of your life believing that a plus b squared is a squared plus b squared. I said this to my calculus class this morning, and I think a few of the students were looking around and they were like, wait, isn't that true?
If you're in a field characteristic too.
Well, yeah. Depends, yeah. So, okay. All this information on the syllabus is on the course website and more. On the course website, I will scan in any documents I write up. When I say documents I write up, I mean these basic slides that I'm going to have here. And I can't tell if I'm zooming in or out. That's zooming in. Oh, wait, have I zoomed in all the way? Okay, let me use. Okay, that's definitely zoomed in way too far. Okay, which way is zooming out? Okay.
I think it's going in.
I think we're going in.
Oh yeah.
Okay, this apparently can only zoom in.
Like one of
in
your pens on the thing.
instead of my.
That's giant.
See that? Now you can see the size as it changes.
It's not actually zooming out.
The camera that only zooms in.
Yes, you're joking, but it's true. It can. It literally is only zooming in.
It's a one-time
I have never seen that before. Okay, this is an unexpected thing.
Try turning it off and back on
Good idea. That's how you
Well-
say to reset.
well-
That's how you zoom out.
Probably something physical.
I should work in IT.
Yes, but now we can at least see the pen in high resolution. Okay, well, we will be bold and try turning it off,
That's how you zoom out. You turn it off.
and then we
So
turn
that
it
can
on,
out.
and let's just see what happens. That's making a noise. It's making a noise. It says Elmo. Hello, Elmo. Hey. Okay, I'm not going to adjust this zoom anymore. Okay, so I suppose any questions before we get into the meatier part of the course, which is today, we're just introduction. Okay, all right. I'm going to sit down because I cannot write standing up. You should always feel free to ask questions. All right, so here we go. Maybe I can risk zooming in a little bit. A little bit more. Okay. All right. So this is spectrograph theory. Now, what is spectrograph theory? Well, a lot of people have heard of graph theory, and they have heard, of course, of was it Spectra? Was the James Bond movie? And there we go. But spectra refers to something else. So our basic philosophy is that we have these 2 worlds here. So we have one world, which is linear algebra, and all the wonderful things that goes along with linear algebra. And almost everybody here has had a linear algebra course since it's a prerequisite. I really hope they have. In the other world, you have graph theory. And what we're interested in is spectrograph theory is this sort of middle region. This is where we're after. We're going to spend our semester looking at these things. So it's going to help to understand what are we looking for from linear algebra, what is it we want to understand, what is a graph, what is graph theory, and then why does it make sense to say that there's even any overlap between these 2 things. So let's talk a little bit about linear algebra. So linear algebra, most people think it's about matrices. And if you ask me, I would say, well, it's mostly about matrices. but it's a little bit more broad than that. So the idea here is that you have this vector space, and I'll mark it here by writing the word vector space. Now what's a vector space? Well, it's a collection of vectors. Okay, well that's okay, that's fine. What can you do with vectors? Well, vectors have three important properties. You can do the following. You can add vectors together. So if I have two vectors, I can add them together. The second thing I can do is I can scale vectors. So if I have a vector, I can multiply it by a number. So I can like take twice that vector or 3 times that vector. And the third thing that's important is this is all reasonable. Now, in other words, given that you can add and that you can scale, then everything that you expect to be true is true. You know, what do I mean by that? Well, as an example, if I take, say, A, which is a scalar, so we represent that with a letter, and U, which is a vector, which again apparently is represented by a letter, so maybe I'll put an arrow here, and I add B times U, it's the same thing as adding A and B together first and then multiplying by U. So these types of things are what I mean by it's reasonable. Things that you would expect to be true are true. So that's not really any big surprise. And so vectors are really, really nice. And vector spaces are very, very nice. But they're, in some sense, it's not very exciting because it's almost, these properties are almost too nice. So when does it get interesting? Well, there's two basic things. First off, you have a notion of a basis. Now, a basis is the following. It's a collection of vectors, and these are vectors inside our vector space, such that any vector, and I'm going to underline the word here, any, to say any vector, backwards e factorial, which actually means this is bad math notation, but exists a unique. So if you ever see backwards e factorial, that's actually supposed to stand for there exists unique. That means there is one, and there's only one way to write as a combination of basis vectors. Now, one of the things I realized I should have done before I finished writing this is I should have said a linear combination of basis vectors. So I can use my fancy colors here. Linear. Now, I probably should have used a fancy color that actually shows up. All right, linear. There we go. That's definitely going to show up. So you'll hear, if you take your classes from further on you go, you'll hear about there's things which are linear, like the derivative is a linear operator. Now, when we take calculus, we never say that to our students because students don't understand what does it mean to be a linear operator, what does it mean to be an operator. But a linear operator is anything where you have a linear means addition and scalar multiplication. That's what linear means. So when I say a linear combination, it means, look, you can scale the things that you want to scale, you can add the things together that you want to add. And so now why do we say that derivatives are linear? Well, because I can break up derivatives over addition and I can pull out scalars. Same things with integrals. Integrals are linear operators. So linear algebra, it's all around us. Everything is linear, which is not surprising. You know, one of the most important lessons I learned when I was but a young mathling, not unlike most of you here, I remember I went in on a class, in a linear algebra class, and you know, you learn the world around us. You know, it's full of bumps and wiggles and squiggles and all sorts of hard things that we don't understand very well. But linear things we're awesome at. We love linear things. We love lines and planes and vector spaces, because vector spaces are awesome because everything's nice. And so what do? Well, calculus is the whole idea of let's apply linearization to understand things. So it's the approximation of things by flat things. And that's a really lousy way to explain that. But if you watch my calculus videos, that explains it much better and with better pictures. Okay, so I'm getting sidetracked. So we have vector spaces, which we can add vectors, do all sorts of things. There's a basis. It's a collection of vectors. Let's give a quick example. So examples are good. Now, almost always our examples have to do with things in finite dimensions, and we like vectors as list of numbers. So I'll do that. So we could say, for instance, our vector space V could be R2, and then I could have my two vectors here, say U, I could have be the vector 1, 1, and V could be the vector 1, minus 1. And I claim that this is a basis, in that there is a unique way. You give me any other vector, I can write it as a linear combination of these two vectors. And in retrospect, maybe I shouldn't have picked these two vectors, but let's go ahead and try this. Does anyone have a favorite vector? 17.3. An unusual choice, sir, but I will indulge you. Okay, so the claim here is that 17.3 is a linear combination of 1, 1 and of 1, negative 1. All right, so, yes. Well, it's not so hard. What are we looking for? We're looking for two coefficients, a and b, so that if I add a and b together, I'd get 17. And then if I took a, subtract b, I'd get 3. Okay, well, is that possible? Well, yeah, the answer is, for instance, if I take a to be 10 and b to be 7. Well, I scale. 10 times 1, 10 times 1, so this would be 10, 10. This would be 7, negative 7. So I get 10 plus 7, that's 17. 10 minus 7 is 3. Of course, did I get lucky? Well, maybe I got lucky in that I had reasonable numbers, but no. You can show that it's unique. Okay. Now, but what makes this interesting? So we have this vector space. What can we do? Well, here is where it gets fun. What we can do is I can take one vector space, call it capital U. I can take another vector space, call it capital V, and then I can look at linear transformations. So T is a linear transform between U and V. So U and V are both vector spaces here. Now I've used the word linear again. Okay, so whenever you hear the word linear in any class, you should think, all right, that means it works really well with addition and it works really well with scalars. So in particular, that says, look, if I have a linear combination, so addition and scalars, AU plus BV, then I should expect that I can pull out any scalars and I can break it up over addition. So that's A times the transformation of U plus B times the transformation of V. And these are operations that we can do. We can add and we can scale in our original vector space U, and we can also add and scale in our new vector space V. So this right-hand side makes sense. All right. Now we're getting to really interesting questions, and we say, okay, how do we understand a linear transformation? Well, the answer is there's lots and lots of ways to understand it. All right, well, how can we represent? I mean, how much information do we need? And the nice fact, and there's a basic fact here, is, look, if you want to understand a linear transformation, you don't have to understand every single vector. It suffices to understand the basis. Now, I used a word there which was wrong. Does anybody know which word I used which was wrong?
V.
Yes, the basis. Why is that wrong? There's multiple bases. All right. And now I'm trying to think if basis is B-A-S-E-S or B-A-S-I-S.
Bases or bases?
Bases or beta.
Basis is with an I.
A singular
Right.
is
Multiple bases.
Bases.
You want
Basis. Okay, there we go. All right. All right, that'll work. Okay, so it really just have to understand what's happening there. Now, we're getting very close to where matrices come into play. But let me point out here that the linear transformation is not a matrix. It's represented by a matrix. You can do a lot in linear algebra without ever referring to a matrix. So let me mention one very special thing. So there's something called an eigenvector. Now, to make sense of this, I want to talk about a very special type of linear transformation. Namely, I'm starting in U, and I'm going to take a map from U back to itself. So it's a linear map from U back to U. So the advantage of this now is I start in one space and I'm ending back in that same space. Okay, so given that that's true, I might be interested in vectors which look really similar to how they started. One might even say the same. And if I were German, I might say eigen, or I'd probably have a much harsher sense. You know, I always imagine that Germans speak very harshly. I think that's just because of all the World War II propaganda films. The Germans always seem upset with each other in those films. But anyways, it's not true. They're not always upset. So eigenvectors are, the idea of an eigenvector is it's a vector which is really nice under the linear transformation. So we'll say if I have a vector x, which is not the zero vector. Now, the zero vector is a very special vector. And now, why do I say that? Well, 0 is your favorite number in mathematics. 1 is a close second, but 0 is your favorite number. And there's many things that's true about the zero vector. If I take any number and I add it to the zero vector, if I take any vector, I add the zero vector, I get back the same vector. It doesn't do anything. It's essentially, if I'm thinking now in things like R2 or R3, the zero vector is the vector that says, look, stay where you are. As I like to tell my Calc 3 students, the zero vector, it's like the art history major vector, in that it's something without any direction in life. You know, it doesn't do anything. Okay, there are no art history majors in this class, so I can make that joke. So what's an eigenvector? I haven't told you that. So an eigenvector says, suppose you have a vector x, and it so happens that when I apply this transformation, what I get back is some multiple of the original vector. Now, this multiple, we use the letter lambda, and I'm not sure why. We don't have to. Any symbol will be useful, and we'll use different letters depending on which context we're in. This is called the eigenvalue. So in other words, what number did you need when you took this transformation? So the moral of the story here is that eigenvectors are intrinsic to the linear transformation. They're not necessarily tied to the matrix, which is, some people think, look, you know, you always have to start with matrices. Okay, why am I talking about matrices? Well, there's a good reason. All right, we're almost there. I claim it suffices to understand the bases. And in particular, what I need to do is I look at how things map. So here's a good rule of thumb. Everything, if we go back to what we said before about a basis, every vector here has a unique representation as a linear combination of things in the basis. Now, what does this mean? Well, it tells me that if I have a unique representation, that I really just need to know the coefficients. So what I can do is for any vector, let's suppose I have u1, u2, un as my basis elements. And if I take any other vector at all, I can write it as a combination, a1, u1 plus a2, u2 up through a and u sub n. So where these u's are all vectors and these a's are all coefficients. And I'm going to assume that we're always going to be working over the complex field or the real field. You can make them over smaller fields. If the mood so struck you, it's up to you. It's up to you. So in particular, what that tells me is that if I want to understand a vector, I really just have to understand the coefficients. And I can represent the coefficients by a column of numbers. And so that's why when we often think about vectors, we think about them in terms of these list of numbers. And what that list of numbers represent is the coefficients. So a vector v is a list of numbers. And now what happens is I fix a basis for u, and I fix a basis for v. So I have this linear transformation, and what will occur is that I'm going to have my vector, which I now represent by a column of numbers, is going to go to, well, I shouldn't, well, okay. It's going to go to a new column of numbers. And depending on the dimension, they might have different size. So, for example, your original space might be n-dimensional, your new space might be m-dimensional. Now, I have no idea why I'm doing so much linear algebra. I think I'm doing penance, because the last time I taught linear algebra, and I have several students who were in linear algebra with me last time, they might remember that I didn't bother to do any of this. I just sort of said, we're going to assume you know all of this, and let's just jump right into matrices. And so now I feel bad that I didn't actually explain all this. And so this is their chance. Of course, they've all passed the exams, and so it doesn't really help them at all. But I feel like I should at least say it once, so that they know I really do know linear algebra. All right. I promised matrices, and now here we go. So what I'm going to do is something very, very simple, and it's the following. I want to understand where each basis element maps to. So I'm going to say that every ui it can be represented as what? Well, it's zeros almost everywhere except in the ice slot. Because remember, I can write everything as a linear combination. So, it's the easiest way to write a basis element as a linear combination, well, it's itself. So it's zeros for everything except itself, which has a coefficient of 1. And now when I take the transformation of that vector, so t of ui, oftentimes we will suppress the parentheses here. Well, what that's going to do is it's going to go to something. So b1, b2, down to b sub m. And now what we can do is we just make the following convention. We can associate t with an array of numbers. So t is going to be associated with the following. So here's, okay, now I see that we're going to get confused in here. But that's mostly me that's going to be confused and not you. You'll probably understand everything clearly. Okay, so what I need to do to make sure that I don't sound like a crazy person is I need to add another set of subscripts here. So instead of saying b1, b2 down to bm, b1 comma I, b2 comma I, because this is a transformation of the ith vector, and so we're going to have different numbers for different entries. Okay, and here we go. What we're going to do is we're just going to collect all of these vectors that we've generated. So in the first column, we're going to have b1 comma 1, b2 comma 1, down to bm comma 1. The second column, similarly, except now it's b1 comma 2, b2 comma 2, all the way down to b sub m comma 2. And we keep going until the last column, b1 comma n, b2 comma n, down to bm comma n. And now what is this array? Well, I'm storing what's happening to each of the basis vectors. And if I know what happens to each basis vector, then I understand the transformation. So in essence, I have completely stored the transformation inside this array of numbers. And this array of numbers is what we call the matrix. This is the matrix corresponding to T. And then in parentheses, we'll put given our bases. I think this is an E basis, because there's multiple bases, because there's two bases involved here. What were our two choices? Well, there's our bases for U, and then our bases for V. So we had to make two different choices for our bases, and then we figured out what happens here. Now, how do we do this multiplication? Well, now it becomes straight up just matrix multiplication in the normal sense. So, in other words, if I want to find what the map does, if I want to find TU, well, T of U, what do? Well, I take this matrix here. Imagine I wrote it down again. And I take these coefficients. So A1, A2, down to A sub n. And I multiply. So it's going to be A1, the result, A1, that says you have A1 times the first vector. Well, what does the first vector do? It does what's in here. So it's A1 times the first column, B1, 1 down to Bm, comma 1, plus A2, B1, 2 down to Bm, comma 2, and so forth and so on, all the way down to A sub n, B1, comma n, Bm, comma n. And everything is represented by matrix multiplication. Okay. Now, I guess I should give an example. So oftentimes, we completely forget that there's this linear transformation in the background. We just say, oh, here's a matrix. Okay, so let's write down a matrix. Let's do maybe 2 by 3. So I'll need some numbers here.
137.
Okay, 1, 3, 7. Good, I need 3 more numbers. Okay, apparently somebody remembered being a TA for my class. All right. Any more numbers?
731.
Okay, all right. 7, 3, 1. All right. So this matrix represents a linear transformation. And we can say a couple of things. What this matrix represents is this is a transformation from a 3-dimensional space down to a 2-dimensional space. Now, how do we know this information? Well, we can read it off because we have the number of columns. That's how many dimensions is in your original space. The number of rows, that's how many dimensions is in your target space. So we're going from 3 dimensions down to 2 dimensions. All right, and now I can pick a vector in 3 dimensions. I will pick 1, 0, 2. Doesn't matter. And I can say that this linear transformation, I can now just do matrix multiplication. So, and I know you all know matrix multiplication, but if I put it here, then I really know you know it. So what are we doing? Well, oftentimes people think of it entry-wise. So it's 1 times 1 plus 3 times 0 plus 2 times 7. That would give you 15. 1 times 7 plus 3 times 0 plus 1 times 2 would give you 9. But you could have alternatively just said, okay, this is the first column times 1, the second column times 0, and then the third column times 2, and then if you combine those together, you'll get 59. All right. Okay, so linear algebra, we have these vector spaces, we have basis elements, we have these linear transformations, and linear transformations are really the interesting part of linear algebra. How do I get a linear transformation from one part to another part? And now we can start saying, look, how do we represent it? We represent them by matrices. And it's nice and compact because you might have a really huge vector space, but it has a nice compact representation. Now, you'll notice that I wrote down that there's a dependence on which basis you picked. Now, what's a good basis? That's a good question. So I'll ask them, what makes a basis a good basis?
What is the definition of good?
Sorry, what?
What is the definition of good in mathematics?
Well, see, there is no definition of good in mathematics. I'm sure there's actually somewhere where somebody defined this is a good sequence if the following are true. But good should mean something that's convenient to work with.
Standard basis.
Well, so like a standard basis, for example, if we're in Rn is a good basis because what makes the standard basis so attractive? It's simple, but lots of zeros is the correct answer because it's all the entries are 0 except one entry, which is a 1. Okay, so that's what makes a standard basis so attractive. Now, in terms of linear transformation, what would be an attractive thing to put into a basis? Yeah. So if you have a linear transformation from a space back to itself, eigenvectors are really, really awesome for linear transformations. Now, why is that true? Well, what's the answer?
Zeros?
Lots of zeros. Okay, all right. All right, good. Seth's looking for the win. All right. See, you should sit up front. Okay, good. All right, now, that's linear algebra. All right, that's only half the story. Remember, there's a second half. There's graph theory. Okay, so let me talk about graph theory for 10, 15 minutes, and then maybe we can tie these two together. Now, the last time I taught graph theory, I have to say I was a little bit in a fun mood that day. And so I carefully defined, okay, let's start off. You have a set of objects. Let's define the Cartesian product of sets. So you have x cross y, and then a graph is a subset such that for any x there's at most one y in that pair inside the Cartesian product. And then I carefully, I was doing all this, writing it down. People were scribbling furiously. Lots of people were like, is this really graph theory? I've never heard of these things. And then I said, okay, let's give an example. For instance, you might have y equals x. And then I carefully plot the function y equals x. And then I couldn't stop myself from laughing because that's not the kind of graph we're talking about. Graph theory is a different kind of graph theory. Okay, anyways. You had to be there. It was fun. It was fun. Kristen said I should do it again because, you're the next generation. I should always do it. I can only do it once every 5 years. But. Okay, so graph theory. Now, graph theory is a really cool thing. And first thing, it's amazingly broad. Amazingly broad. Well, it's always dangerous if you have something that's amazingly broad. It's probably not very useful. But it's still good. You just add enough constraints and now it's useful. Okay, so what's a graph? So a graph has two things. So a graph is essentially two sets. And we almost never think of it this way, but it's good to think of it. So the two sets are V, which stands for vertices, and in some areas they call these the nodes. And this is just a collection of objects. It can be any object you want. And this is why graphs are so cool. It can be, your vertices could be the numbers 1 through n. Your vertices could be themselves vectors. They could be functions. They could be people. If you want to make $1 million, that's not cool. What's cool? $1 billion. You want to be Google. What graph do you care about? You care about a graph that's the internet, in which case your vertices are web pages, and you want to look at things. Okay, so that's the first half. The second half is your E. Now, E here stands for edges. And edges are your connections of objects. So in other words, I have these sets of objects, and I want to connect them together in some way. The way I often think about graph theory is I say, okay, well, I have a collection of things. Which things are connected to each other and tied together by some rule? I want to say those are my edges. Now, I'm going to say here that there is a lot of different kinds of graph theory, and one of the first places where you start making distinctions is what an edge is. Because a vertex is a vertex. Okay, it's just a collection of things. But a connection, okay, what are some things you might see? Well, you might see something which is called a simple graph, and that's a very simple relationship, hence the name simple graph. It's essentially, I like to think of it as a 0-1 relationship. It's either there's a connection between them or there's not a connection. So you're either connected or you're not. There's no sort of fuzziness to it. And the other thing about simple graph is that you have symmetry. So in other words, if object A is connected to object B, then object B is connected to object A. Okay. So a simple graph, 0-1, symmetry. Another thing you could do is you could do a weighted graph. Now, a weighted graph, well, now your weights are more arbitrary. So they don't have to be 0 and 1. They can be any reasonable number. Most of the time we assume our weights are non-negative because we like to think of things oftentimes in terms of flow and capacity. Like this edge indicates an amount of capacity between two vertices, like how many cars can go between two cities, how much water can flow down some pipe. It's harder to get an intuition for -1. But we still have symmetry. You can also do what are called digraphs or directed graphs. And digraph, we'll start with a simple digraph. Well, that's 0-1, but you no longer have symmetry. It might be A can go to B, but B can't go to A. And so this is one of those sort of awkward things when it's like somebody says, hey, you're my best friend. And you're like, oh, that's nice. And you don't have the heart to tell them, you're not my best friend. That's an example of something where you don't have symmetry. Okay. You can also have weighted digraphs, in which case you basically, all bets are off. You don't need symmetry. Weights can be arbitrary, and so forth and so on. You can also, of course, to all of these, there's a question of whether or not you allow loops or no loops, and which gets into a whole other discussion. And this is not even the full story. you can go even further and you can say, well, what about hypergraphs? Well, hypergraphs, this is where edges are now not just collections or connections between two objects. You can have connections between multiple objects. So edges connect multiple objects. So for example, now edges might be 3 vertices or 4 vertices, and so forth, and so on. Okay, so this is what graphs are. So it's a set of vertices and a set of edges. All right. Well, how do you think about graphs? Almost nobody thinks about a graph by saying, a graph is 2 sets. They almost always say, oh, let me draw you a picture of a graph. So what do? Well, we usually represent our vertices as points or dots, and I'll draw a graph, and then we connect them. So for instance, I might have a graph where I have connections in the following. So this is an example of a graph. This is a graph that will play a role in a lot of our discussions going forward. So it has 6 vertices. You can count. There's 3 along the top. There's 3 along the bottom. 3 plus 3 is 6. And then I have a lot of edges. And the edges are drawn here. Now, don't get too caught up on the picture, because I can change the picture. For instance, perhaps I draw, instead of 6 vertices, 3 on top, 3 on the bottom, I might draw them in a circle. So, all right. And then I'll put edges around the circle. Okay, that's not so bad. So that's another graph. Let's add a couple more edges. Let's add edges going across and joining opposite vertices. Okay. So this is another graph. Or is it? Are these 2 graphs the same, or are they different? What was that? They're the same. Oh yeah. I thought this was going to be more challenging to people. Okay. Well, let me try to convince you. In 1, 3, 5, 2, 4, 6. So I'm just going to number the vertices, and over here I'll number them going around the circle. So in the first case, I labeled the top 3 by odd numbers, the bottom 3 by even numbers. In the second case, I just labeled around, and you can check that 1, or rather I should say any odd number, not just 1, is always connected to every even number and vice versa. Okay, so what's the story here? The story is that graphs can be represented pictorially in many, many different ways. So don't get hung up on whether or not what the graph looks like visually. This is just a representation. Now there's a fantastic question embedded in this. How can I tell if I have 2 different graphs? How can I really distinguish graphs? And the answer is that's hard. Now, it is known, and this was just proved within the last few months, that you can do that in sub-exponential time. So if you have a graph on 1,000,000 vertices, it takes less than e to the million to figure out whether or not those 2 graphs are the same or different. Now, the truth is, most graphs are different. And how can you tell? Well, one of the ways you can often rule out really quickly if 2 graphs are different is using linear algebra. Now, we are at the end of today's time, which is a shame because we were just about to get to this interesting part here. So we've talked about linear algebra. Linear algebra has these transformations, which are going to represent by matrices. We've talked about graphs. Okay, let me just briefly, in 60 seconds, say why do we expect there to be a connection? Well, we expect there to be a connection because of the following. When I think about a linear transformation, well, what I really have here is I have each row and each column is tied to a basis element. So in other words, I'm indexing by basis elements in matrices. And when I'm saying, well, how do those 2 basis elements relate to each other or connect to each other? And I say, well, wait a second. Something similar is going on here when I talk about edges in a graph. Because edges in a graph say you have a lot of vertices. And how do vertices relate to each other? And so what we can do is we can say, well, let's store the graph using a matrix. Now, it's a little bit different than saying let's store the graph using an array, because an array is a collection of numbers. A matrix has an interpretation. It's a linear transformation. And we're going to see that adding on that extra layer of linear algebra is going to give you a lot of information. So next time we'll get into a lot more specifics. We'll start going into it, and a lot less linear algebra. So, and that's it for today. See you on Wednesday.